So yesterday, the last thing we said were these two theorems, which are equivalent, and this is called the compactness theorem. In its first version, it says that if you give me an L theory T, then this theory is going to have models if and only if every finite subset of this theory has models, right? And the interesting implication, of course, is this one. This one is trivial, and this one is now interesting because then we can build models out of just checking that we have models for finitely many sentences at the same time, right? This is a nice task. And in this case, well, they're equivalent, but it says that if some formula is a consequence of a theory, then it has to be already a consequence of finitely many sentences in this theory. Okay. Now let me give you some applications of this so that you can get the flavor of how powerful this can be. Let me first of all prove you the upwards Lovingham's column theorem because we didn't prove it. Let me give it the proof for this. So proof of upwards Lovingham's column. Okay, so recall that this was stating that so if I have a structure M and L structure, right? And kappa is a cardinal, right? And kappa a cardinal, right? A kappa cardinal, such that kappa is bigger than the maximum of all these M, aleph 0, and oh, sorry, I can also put this here just L, but I'm assuming that M is infinite. If M an L structure and kappa cardinal such that this with M infinite, okay? I'm taking already an infinite structure, okay? Then we need to consider, right? We need to construct, we need to show there is some elementary extension of M of size kappa. Right? This is what we need to show, that we can go up to kappa. We can find large elementary extensions of M, right? Right. Then, actually, I can take here also a kappa, which is strictly bigger, right? Because if kappa is exactly the size of M, well, I can take M itself. So this is a little bit silly. So we can take kappa to be bigger. Okay. So the way we do this is the following. We consider a particular theory. So consider the language, let me call it LM, which is just exactly the language L, but I'm going to add to this language a constant symbol for every element in M. Okay? So I add a lot of new constant symbols, right? And we assume that none of these constant symbols is in L, right? New constant symbols with new constant symbols. Okay. So this is an extension of my language. The only thing I added was just a bunch of constant symbols, okay? And now we consider the structure. Actually, let me be more precise, the LM structure M, right? Which is just M, and I'm going to interpret each constant as the corresponding element in M, right? It's just I'm really expanding M and having constant for every element in M, right? The LM structure M, where every symbol from L is interpreted as in M, and we interpret now each of these constants CA in this new structure, right? This is just the element A, right? So for example, if the starting structure was the real numbers, what I'm saying is that I am in a constant for each real number, and in the real numbers, I'm interpreting this constant by exactly the real number the constant is indexed with, right? So this is nothing complicated. It's just the same structure, but now I have a constant. I have a name for every element in M, right? Now note, this is an observation exercise, is that if I have a model N, and with all this interpretation for all these constants, which is a model of the theory of this structure Mn. So suppose I have another structure, right? Another structure, but this structure is a model of this theory, of the theory of this set. This is a theory in the language LM, okay? If we have this, then M, well, let me say it like this, then there is an elementary embedding
you just want to say that N is a model.
This thing?
That this is a structure for the new language.
Exactly. I'm saying this is a structure for the old language. I am saying I have also constants, right? Yes, exactly.
The new language needs to.
Absolutely,
So
absolutely.
you need to say it is a structure for the new language.
That's correct. But then what I want to say here is that there is an elementary embedding, let's say H from N to N, right? And N is only an L structure. This part is only an L structure. Okay? And this is not difficult. Essentially, the idea is that you're sending, if you're a theory of this, basically sending an element in M to the right interpretation of C of A here is going to be the function that you want. So the idea is show that the function H sending H of A to be the interpretation of this element in N. Let me call this N prime if you want. To N prime is an elementary embedding. Okay? You need to show. You have, for every A in M, you send it to how you interpret the constant CA on this structure. Okay? And if you are a model of this theory, this is going to be an elementary embedding, basically, because this theory contains all the formulas already with constants for elements in A. This is not too difficult, okay? So it is enough to show that the following theory has a model. Let me call this theory now T, okay? T is going to be the whole theory of MM union, and here I'm going to even expand the language a little bit further. So let me say perhaps what is the language first. You know that the following theory has a model. Okay, let me give you the theory, and then let me say what the model should be. I'm going to add even more constants, okay? I'm going to add constant symbols. Let me call them E, okay? I'm going to add a, okay, let me write it like this. E of I different from ij for I and j smaller than kappa. Okay, where all these symbols ei for I smaller than kappa are new constant symbols. Okay? So this means that the language that is the language of this new theory T, the language of T is, let me call it a language L prime, which is all these Lm together with all these new constant symbols, right? Where these are constant symbols.
So it is enough after an application of the downwards.
That's correct. That's correct. Well, it is enough to have. I totally agree. If we, well, let me specify. It is enough to show that the following theory has a model. You're right. I agree. Absolutely. Because this, well, let me say what Javier is saying. Indeed, if we have a model of this theory, let me call it n prime prime. If n prime, let me call it n prime prime, right? N prime prime equal to this model is some n which has some interpretation for all these variables in M, but also has some interpretation for all these EI, right? Smaller than kappa. If this is a model of T, right? If I have something like this, which is a model of T, right? Then since I am a model of this part, I need to have at least kappa elements, right? Because I need to interpret all these constants, and these sentences are saying that the constants are different to 2, right? I mean, there are pair with disjoint, right? There are different elements, all of them, and I have in total kappa of them. So this structure has to have at least kappa elements. I don't know, perhaps more, but at least it needs to have kappa elements. All these elements here that I am interpreting, they need to be different because I am a model of this part of the theory, right? Is this more or less clear? So then the size of n prime prime has to be bigger than kappa, right? And by the observation, there is an embedding H, elementary embedding. Let me put it like this. There's an elementary embedding from M to this, to the part in L, which is N, right? You agree? Size of here, I can delete this, right? So to find one which has cardinality exactly kappa, we go by downwards Lovingham's column to get the right cardinality. Perhaps this is much more bigger, right? We only know that there is a model. We only know that it has at least kappa elements, but it could have, I don't know, cardinality much bigger than kappa. But then we can use the downward Lovingham's column to get exactly kappa, right? Then by downwards Lovingham's column, we can find one of cardinality exactly kappa. Okay. So the whole trick is to show that this theory has at least one model, right? Because if we have one, we find a way to elementary embed M into this model, and this model needs to have at least kappa elements because we have kappa constants, and the theory says these elements are pairwise different, right? So how to show that this theory has a model? We use compactness. Now we only need to show that every finite bit has a model, but this is an easy task. Is there a question? Are there any questions? This is a key thing to understand properly. So if you don't understand a bit, please say it. Yes, Richard.
So the observation, the point of the observation is we can take any. Are we supposed to start with an L structure and then? No, but the N.
This one.
Like, yeah, this one is an L structure, and then you just throw in
The interpretation of
lots of constants.
exactly.
But what we want to use, in fact, is something with a constant for every
Element of
lower than k. So I mean,
well,
we're trying to plug in the observation. Are we trying to plug in this even bigger n?
so in the observation, we're plugging a constant for every element in M, right? And we know actually M is smaller than this kappa, so this is no problem. The observation, the point of the observation is that by being a model of this theorem, of this theory, then I am ensured that if I forget the constants, I can still find an elementary embedding into the L structure part of this L M structure, right? So.
Okay, but now but I mean, we're adding. There's a step where we're adding yet more constants.
Exactly. Exactly.
I don't quite get,
I tell you. So this part is just to ensure that we can embed a model of this part into M. Sorry, that M embeds into this model of N. And this part is to ensure that this model is going to be of a given cardinality, right? This part is only to ensure the observation. So whatever is going to be a model of T prime, because it is a model of this, I'm going to be able to embed M into this structure, right? And this part is going to ensure me that the model is going to have cardinality very big, at least kappa.
Not with the extra.
Not with the extra. The observation only stops here.
Okay. And so we just have all of these. It feels like cheating, right? I mean,
it is. Okay. We're kind of really cheating. It feels like cheating, right? But it is difficult to show without compactness that this is going to have a model. I have no idea how to proceed, right? I mean, how can I show just that this bunch of sentences in the new language has a model at all, right? This is where compactness, I mean, we haven't shown this. This is just for the moment. What I have said is that if we manage to show that this has a model, then we're done. Because a model of this, I'm going to be able to embed M into this model, and it has to have cardinality very big, right? And then we can find by downward Loppingham's column one which is going to have the right cardinality. But we still need to show that this has a model at all. I have no idea why. And this is what we need to do with compactness, right? So by compactness, we know that it is sufficient to prove that every finite subset of this theory T has a model, right? And this is what we are going to show. So by compactness, it is enough to show that every finite subset T0 of this T, right, has a model. Then let's take a finite piece, right? Let's take T0 every surface. Yeah, fine. Let T0 be a finite subset. Right? Then it contains a finite part of this theory, right? Just finitely many sentences here. But more importantly, it contains only finitely many of those inequalities, right? This? Yes. This is the, I recall you. Perhaps I can write it here. TH of MM is the collection of all phi, right? Such that phi is an sentence in the language of this theory, which is this language, right? is an LM sentence where I already put all these constant symbols for elements of M, such that this structure satisfies the sentence phi, right? Is the collection of all sentences that hold in this structure, right? And you need to use this to show this observation, this exercise. Of course, you need to understand properly what this means, right? So in particular, let me give you a hint. Of course, if, for example, phi of x is an L formula, and n satisfies phi of a, let's say for a equal a1 up to a n in m to the n, right? Yes. Then this implies that the formula phi ca1 can, this is now a sentence in this language, is a member of this theory, right? Because it means if this model satisfies this formula, exactly the same thing, but replacing the elements by new constants in my new language has to be true here. Well, has to belong to this new set, to the theory of this new structure. It might be a little bit puzzling, but think of it for a while. If what I'm saying, perhaps it's easier if you think it in a particular structure. Take your favorite field. Take the complex field, right? Then on the complex field, the L-ring formulas, we said they have no parameters. I cannot say something for pi or for e. They have no parameters at all, right? We were saying the only polynomials with coefficients I can use are coefficients in Z, right? In this new theory for the complex numbers, I'm adding constants for every complex number. So now in this theory, for example, I have really all polynomials. I can use coefficients in C, right? Because I added constants for every element in C. So if a formula without, just in a formula in the language of rings was true for some elements in C, now in the new language, I have an actual sentence because I added all these constants for every element in the complex numbers, right? So yes.
And would you then get like new sentences, like in for example, like would you get new sentences like
Absolutely.
Like there does not exist, the sentence for a degree n polynomial such that E satisfies the.
Absolutely.
Okay.
Absolutely. Absolutely. I get a lot of new sentences, right? I mean, this is a much richer.
Like everything that can possibly happen
in the complex numbers.
The actual numbers themselves.
Exactly. Actually, right. This theory, for example, if E and I happen to be algebraic dependent, this theory should know it by a sentence, right? It's there, but we don't know. but the theory contains, for example, a sentence denying this or depending if it is true or not in the complex numbers, but we don't know. Right? Okay. But this theory contains just everything that you can possibly say about the complex numbers in a sentence in the language of rings, because you have constants for every complex number. Okay. Right. So of course we have no idea really how this theory looks like, but it's just for the moment a set. We are just using it to get an embedding from C to somewhere, or in this case from M to something big, right?
So this theory contains theorems that we didn't prove yet.
Exactly. Absolutely. Absolutely.
We should go one by one.
No. Be careful. This is not countable because we added constants for every complex number.
I was thinking of C, but
C is uncountable. Right. So this theory contains theorems that we will never prove, I guess, if we believe computers just, I don't know, just compute countably many things. This is a huge set. I mean, we cannot. Okay. But let's nevertheless prove that this is consistent, right? This we can do even if it is a huge set. Yes.
So, isn't M itself?
Exactly. Eki just solved the problem. M is going to be a model of T0 because the only thing that we need to show is that we can interpret these constants in such a way that this is true. But since we have only finitely many of them and M is infinite, well, M is going to be a model of this. Exactly. So actually, right, let me write what Eki just said. So take a finite subset. So let's say EI1 up to EIK be the constants that appear in this finite set, because since it is finite, only finitely many of these are going to appear in formulas, in sentences, right? So let this be all new constants from this set that appear in T0, right? Then, of course, T0 is included, right? This T0 is going to be included in the theory of MM union all those possible formulas with constants here, right? So I write here E I different than ij for I different than j, and these two elements in this list of indices, I1 up to Ik, right? I mean, T0 is just a subset of, well, for sure of this part, union all of them, but the fragment of this, which appears in T0, has to be included in these ones because these are all the constants that appear here, right, in T0. But now M has to be a model of this, right? Let me say it like this. Interpreting let me put it like this. Since M is infinite, take A1 up to AK elements in M and interpret different, right? Different elements. Now interpreting the new constant E I sub S in this new structure, right, in M, and you call it M prime, or if you want, as the element AS, well, gives a model of this theory, right? Because the whole of M for sure is going to be a model of this part of the theory. And now, well, interpreting these elements like this, since they are different, for sure they're going to satisfy this part of T0. Hence, T0 has a model. Okay. Is it more or less clear what we're doing? So compactness is very strong. You only need to satisfy finitely many pieces in order to perhaps obtain a model which satisfies a lot of them at the same time. This is something nice. Okay. Let me give you another application. So this is the proof of the upwards Lovingham's-Collin theorem. Let me give you another very nice application. Is this clear? Is there any other question on this proof? Perhaps let me also, no, let me still have the two statements of the compactness theorem then. And I'll give you a baby form of what you will see next week. This is a transfer principle. This is called the Lefschetz, kind of first order Lefschetz principle. It's a nice result. This is just an application of compactness. For this, we need to recall a little bit about how some theories were defined, but you will see, when you see the proof, you will see this is easy. So theorem, it's called Lefschetz transfer principle. Let's say first order, because there are other transfer principles which are perhaps a little bit strong. It says the following thing. The following are equivalent. Equivalent for phi an L-ring sentence. So take a sentence in the language of rings. You have the following. Let me have them in the order I want to for the proof. This is perhaps nicer this way. Yes. So the theory of algebraically closed fields of characteristic 0 implies this sentence. The second one is this sentence is true for the complex numbers. And this is the more interesting part, is the theory of algebraically closed fields of characteristic P also implies this sentence for sufficiently large prime P. And 4, let me put it like this, the algebraic closure of FP also satisfies this sentence, again, for sufficiently large prime P. So this is a transfer principle between characteristic 0 and characteristic P. We're saying a sentence, let's say, holds in the complex numbers if it holds in the algebraic closure of FP for large prime P. It's interesting, right? We're saying that somehow the complex numbers are, to some extent, asymptotically behave a little bit like these fields as well, right? Let me show this theorem. So this is a way of transferring things that you know in complex geometry. Well, things no. Of course, something which is expressible in the language of rings. This is restrictive, of course. For this is why this theorem is a baby transfer theorem. Of course, you would like to transfer, I don't know, sentences which talk about homotopy or homology. This is not the case, right? But at least you're giving an idea of how perhaps could work a transfer principle. You just need to be very patient, define some language in which you can express this, and then perhaps prove some complete, or some theories complete. These are by far not easy results, right? If you manage to do this, then perhaps you can have something like this. But at least you're getting the idea of how a transfer principle might be achieved, okay? So in this case, this is going to be not too difficult to have. Proof. So let's do 1 implies 2. So 1 implies 2, this is just the completeness of this theorem, right? Or, well, this is just because this is just the fundamental theorem of algebra, if you want. This is just because C is an algebraically closed field, right? This is just because C is a model of this theorem, right? So if we're assuming this means that any model of this part has to be a model of phi, and we know C is algebraically closed, then it has to satisfy phi, right? This is just knowing that C is algebraically closed. Okay. 2 implies 3. Here we need to do something, right? Here is the passage where we know something is true in C, and then something is going to be true in characteristic P. right? Me. Okay. Then, because this theory is complete, right? We know this theory, we proved this theory was complete, right? Yes.
Just to recall, like that, we basically used that as Q vector spaces.
No, this was with the transcendence degree. This was Steinitz theory, right? We proved that this theory was categorical for any cardinal bigger than ellipse 0, right? And then this was using these transcendence basis. And because it is categorical, it has to be complete, right?
We say ACF0 or
ACFP for any prime or 0, right? Because the proof.
require infinite field?
Absolutely, any algebraically closed field has to be infinite. But this is a good observation. I think we didn't state it yesterday. In order to apply Vought's criterion, we needed that we only have infinite models and to be categorical. But every algebraically closed field has to be infinite. If you don't know this, think about it because it's a nice exercise. Okay, if it is of characteristic 0, easy because you have the rationals inside, but if it is of characteristic P, you need to do a small argument to be sure that no finite field is algebraically closed, or right. Okay. So we know that this theory is complete, right? So if C satisfies this sentence, it has to be implied by already this theory, right? Because it cannot happen the contrary. Then ACF0 has to satisfy phi. I mean, it has to be an implication because since it is complete, this happens, or this one would imply the negation, right? But if it implies the negation, this would contradict that C is a model of phi, right? Let me say.
Because it is complete and two models are elementary equivalent.
Exactly. Let me not write it.
You wrote this then.
Absolutely. If not, I will have then a model which satisfies the other, and then it would not be elementarily equivalent to C. Whatever way you want to show it, if let me say it like this: if you have a complete theory and a sentence is true in a model, it has to be true in every model, so it has to be implied by the theory. Okay.
And then when you did 2 implies 1.
Sorry?
You just did 2 implies 1.
That's correct, but I won't use it. But that's true. This basically shows that 2 implies 1.
And I guess now you're going to do about 1 implies 3.
That's correct. But I didn't wrote it this way. But you're right.
Okay, so knowing that the first theory is redundant, then why?
I agree.
This are automatically.
This shows
So they are complete. It's a complete theory. Then the 1 and 2 are redundant.
exactly.
3 and 4 also.
I agree. This shows also 3 and 4 are equivalent. I totally agree. This shows already 2 implies 1, but what we really want is to prove 3, right? Now, by compactness, these two, compactness 2, let's say, there is a finite part, a finite subset of this one, right? Subset sigma 0, let's say, of this theory. Yes.
So C and FP bar are models of the theory.
Not of this one, because this is of characteristic 0, and these are characteristic P.
Yeah, right.
And here is where the magic happens, right? By compactness, I'm finding a subset, finite subset of this theory, such that sigma 0 already implies my sentence phi, right? Now, if this sigma 0 is finite, then I can only say that I am of characteristic different than 2, different than 3, different than 5, different than 7 for finitely many primes. Right? Because recall this theory was the theory of algebraically closed fields, but also saying that I am of characteristic 0. And saying that I am of characteristic 0 was an infinite set of sentences saying I am not of characteristic 2, not of characteristic 3, not of 5, and so on. Right?
Did you actually get proof?
No. This was the definition of this theory. We defined this theory. I mean, our definition, right? This is we define it like this. It doesn't matter, right? I mean, we define ACF0 as the axioms for fields, right? These axioms for saying that every polynomial of degree D has a solution, right? This was also an infinite set of formulas, right? But also union a formula saying 1 plus 1 plus 1 is different than 0 for every P.
I guess what my question was really, is there an equivalence theory?
Right. We didn't prove that we need all these axioms, but we can do all this also by compactness. We can discuss this later. Yes.
So this is just a general like question / observation. So we define this theory, right?
Exactly.
And based on this definition, we were able to prove that it's complete.
Absolutely.
And once you know it's complete, then you can just it's basically you can replace it with just the set of all true sentences.
If you would like to.
You can think of that as what we defined, or just everything that's every sentence which
I agree.
It's complete.
I agree.
Okay.
I agree. But in particular, this will be useful for what we're saying here, right? Because, well, you can anyway. You know that there is going to be this set is going to be finite, so for sure it's going to contain only finitely many of these sentences, right?
Okay, but what if there is an equivalent way of stating the same thing such that we are not using? I mean,
it doesn't matter. I mean, we will show that this is not the case. You can show that this is not the case, but for the proof that I'm going to give here, it doesn't matter. Note, this is important. Note that this is our definition for ACF0, right? It was all of these sentences, but for ACFP with P prime, right? P bigger than 0 prime. This was exactly the same. The first part is the same because these axioms didn't change. Those are the axioms of field and saying that every polynomial, monic polynomial of degree D has a solution, right? These axioms are exactly the same. The only point where these two theories change is in the characteristic, right? Here I need to say 1 plus 1 plus 1 is 0 for P, right? I really need to say here I am of characteristic P, but the only place where they change is that here I need to negate all of these sentences, right? Now, then sigma 0, well, let Q, let's say, be a prime bigger than any prime P, such that the sentence 1 plus 1 plus 1 different than 0 for this length P appears in sigma 0, right? Since this set is finite, I contain only finitely many of these formulas. There has to be a prime Q such that it's bigger than all the primes for which this sentence appears, right? But then this means that sigma 0 is contained in ACF Q, let's say Q prime for every prime bigger than Q, right? And if this one is a consequence of this one, for sure it's going to be a consequence of this one, right? Hence, ACF Q prime is also a consequence of this one, right? Yes.
so Sorry, because I'm still thinking on this thing.
Yes.
So the thing is that if being characteristic zero was one sentence,
Then we're
this I think
exactly.
we
But
still haven't proved. But if it was one sentence, it would be a theorem of this.
I agree.
theory.
I agree. So
And
it
then
better
by
not.
Second compactness.
I
there
agree.
would be a finite set of.
I
There would be a finite set of sentences.
I mean, if it was expressible by one sentence, then I agree. This is bad. But this cannot happen. Again, by compactness. Let me perhaps show it here. Can I delete perhaps the two compactness version? I think so.
But I guess you definitely need to prove it before you say that. That's
Well,
the point, no?
no. I mean, the proof that I just wrote is clean, right? I mean, because those are just, this is a set of formulas as of sentences. This is also a set of sentences, and I mean, the proof, I don't think it needs anything else.
Okay.
But we can show that, for instance, the theory of fields of characteristic zero cannot be axiomatized by one sentence. And this is not too difficult, because if, say, just the fields of characteristic zero, let's forget that they're algebraically closed, just fields of characteristic zero. Suppose that this collection of sentences are implied as just one sentence, right? Then, so suppose that there is psi, a sentence in the language of rings, such that psi, if I am a model of this psi, I am a model of all of them, of fields, and also of I mean, of these, and psi also implies all these formulas. I mean, this one, not zero for each p, right? Right? But then it's also true that this theory, let me call this theory, well, let me write it like this. Phi fields together with all these formulas. Shall we call these formulas differently? Okay, doesn't matter. Also implies this psi, right? Because we're saying this formula is such that if I satisfy it, I am a field of characteristic zero. So this says if I'm a field of characteristic zero, well, I need to be a field of characteristic zero. But by compactness, this sentence is going also to be implied by only finitely many. This is compactness again, right? Then you know that this is going to be fields union only finitely many. This is, sorry, this was a set for every p, right? But now this is the same set, but only for p smaller than certain q, right?
And you will find an element on the left side.
Exactly. You can find here a field of size the next prime bigger than q, which is of course not a field of characteristic zero. So this cannot hold, right? So by compactness, you can show that this needs to be an infinite set of sentences. So the magic here is happening here, right? I mean, this is where we're using something interesting.
Yeah, because when you say this sigma zero here, sigma zero is a subset of ACFQ. I mean, you know what's in sigma zero, so no wait.
Well,
yeah, like you know what kind of because of what was the definition of ACF zero, you know what you're. But anyway, I think I understood. That's the point.
Okay.
I think I got it. Thank you.
You see more or less the point. I mean, the idea is that since this sentence here, it's being implied already by finitely many sentences from this set, the finitely many sentence only can say that you're not of a given, up to a given characteristic. But then for characteristic bigger, every such algebraically closed field is going to be a model of sigma zero. Yes.
So in the last step, you have sigma zeros containing that other theory, and then this implies that the other theory implies.
Yes. Let me show why this is true.
So for this, you need to do something like that again, right?
No.
To know that the mixed sequences in ACF triangle.
No. Because this is easier because so this is the following. This is this exercise, right? Exercise. If sigma is a subset of T and sigma implies phi, then T implies phi, right? Because this is easy since take, right? Take a model M of T, then M, if M is a model of T, then M is a model of every sentence in T, in particular from every sentence in psi, right? So M is a model of sigma, right? And we use this, hence M also is a model of phi, right? This is easier, right? Okay, so we prove, yes. Yes, this is the theory of algebraically closed fields of characteristic 0, right? This is a field of characteristic 0, so it satisfies this part and this part. And the fundamental theorem of algebra tells you that the complex numbers are algebraically closed. So it also has to satisfy all these sentences. Recall I said these sentences were the sentences saying that every polynomial of degree D, monic polynomial of degree D, has a 0, which is not constant, right? Well, it is monic, so.
But maybe this symbol I confused again.
Right.
Is this zero in C or the other?
No, this is not implication at all. This is a structure. This is, I'm using C to denote the structure. This is structure. So this is an L ring structure. I'm treating the complex numbers as an L ring structure with the canonical interpretation for plus, minus, the product, and 0 and 1.
So this means that CSF ring structure satisfies the actions of
Exactly. What this means is that the complex numbers as an L ring structure satisfies exactly this list of sentences, right? Exactly. Thank you. Okay, now, well, 3 to 4, you already say it, perhaps let me, 3 to 4 is again, this is easy, exactly. And well, 4 to 1, let me do 4 to 1. You do the same with negation. You do the same. With negation of phi. With negation of phi, right? If you want to prove 4 implies 1, you can start saying that if 1 does not hold, then ACF 0 must imply the negation because it is complete. Then you go up to here with the negation and then up to here with the negation, and then you're done, right? This is exactly the same proof. Okay, so that's a nice theorem. At least, okay, we haven't really applied to something interesting, but at least you're getting how to perhaps transfer a property that you know for characteristic 0 to characteristic P, right? Or a property that perhaps you know for characteristic P. It happens, both happens. If you're doing complex geometry and prove something for polynomials over C, then suddenly you're also knowing something for the algebraic closure of FP for large prime P, right? And the same holds sometimes the other way. If you suddenly know something it happens for sufficiently large FP, the algebraic closure of FP, then you're actually proving something about the complex numbers. That's nice. Let me give you one. I won't do this in detail, but let me give you One of the nicest application of this one. Even if it seems silly, but the application is nice. This is called the Axe-Grothendieck theorem, and I won't give you all the details because it's a bit annoying to write them, but I'll sketch you the proof. To be honest, I am not completely sure why Grothendieck got his name into this term, but he always, right? Perhaps.
It was first proved by Gutenberg, and then Axe found this nice.
Okay. As far as I know the history, I haven't read the proof of Grothendieck, but Borel saw the proof of Axe, which uses Model T, which is the one I'm going to give you, and he was pissed off and gave a geometric proof, but this geometric proof is not simple. But which is strange, which means that Borel perhaps didn't know Grothendieck proved it on the first time. I mean, at first. So I haven't read the proof of Grothendieck. So it says that let F be an injective polynomial map. Right? This means that on each coordinate, this map is given by a polynomial, right? Yeah. It sends x to p1 of x, pn of x for pk a polynomial in Cx1. Okay. Then F is surjective. Every injective polynomial map has to be surjective on the complex numbers. An interesting theorem, right? And what we're going to show is that actually this is true always here. This is true in every FP for every P. Proof sketch. I mean, I'm not gonna. The first step is to convince yourself that for every degree D, for every degree D, there is an L-ring sentence saying that if F has degree smaller or equal than D, smaller or equal than D, if it is injective, it is surjective. If it is injective, it is surjective. So this is a long formula. I mean, this is a long sentence to write, but it can be done. You just quantify over the possible coefficients. You just put a for all, big, large, for all x, I mean, for all y1 up to for all y n, for a big n, right? You're quantifying over all possible coefficients of a given polynomial of degree d in all these variables. And then the formula says, if it happens to be injective, it is surjective. But this is possible to write in a sentence. It's a long, long sentence, but you can write it down, okay? So this can be expressible. So this means that if we manage to show, let me give a name for this L-ring sentence. Let me call it phi d, okay? This phi d says for every polynomial of degree, for every d, every polynomial map of degree d, right? Right, every polynomial, this is a polynomial map, right? F is a polynomial map. If a polynomial map of degree d is injective, it has to be surjective, right? So if I manage to prove that this sentence phi of d holds for each of these fields, then the transfer principle implies that it holds for C, and then we're proving the theorem, right? So by the transfer, I mean, let me call it step 2. By the transfer principle, it suffices to show that for every d, fp alg satisfies this formula phi d. Actually, for every p, we don't need to show it for sufficiently large. This is actually, it actually holds for all, right? But if we show it for all in particular, we will get it for the complex numbers. This is almost clear, right? Yes. Exactly. This algebraic closure, you can show this is actually the union of finite fields. It's the union of all fields fp to the n, right? So if this was not true, this is going to be not true in a finite field, but in a finite set, every injective function.
You have to, there is a subset, you need to take R, the finite field big enough to contain non.
I agree. But this is still a finite extension because we're algebraically closed. Exactly. Let me write perhaps a little bit of the details that Javier is saying. He saw it too fast. But that's exactly what we do. So suppose not, right? Suppose this is not true. Right. Suppose f, the algebraic closure of P does not satisfy this formula phi d. And let me call it F from Fp alg to the n, Fp alg to the n be a counterexample. Right? You have a polynomial map which is injective but not surjective, right? Then let me say alpha 1 up to alpha k, all the coefficients in all these polynomials p1 up to pn, like here, right? F is the map sending, well, let me say in F, right? In F. And take some element, what do I want to say? And take some element, so this function is injective, but it's not surjective. And beta to be in Fp alg to the n, which is not in the image. Right? Then now you consider this extension. Consider the extension of Fp extended by all these alpha 1, alpha k, and beta. Right? So those are the coefficients. This is the witness of this is not being injective, right? Not being surjective, sorry. And I restrict now.
But it is shorter.
It is shorter?
Yes.
Okay.
Once you have all the coefficients,
Yes.
you take the minimal R, the minimal FPR that contains the coefficients.
Yes. This is this one.
A mapping from FPR to FPR. Since
I agree.
It is injective, it is bijective.
I agree.
And
Okay.
this is for all R.
Yes. Well, I'm doing the same thing, but just by contradiction, right? But this is the same. I agree. So I'm saying there is one which is not in the image, but in this one it's going to have an image, right? The point is that this extension because all these elements are algebraic, this is a finite extension, right? So this extension here is finite, since it is an algebraic extension, right? If I'm taking elements in the algebraic closure, all those elements are algebraic over FP, and an algebraic extension is a finite extension, but this is finite, so this is a finite field, right? But in a finite field, every injection has to be surjective because this is a finite set, right? So beta has to have a preimage, which contradicts that it was not having a preimage here. So this is going to be true in every FP and hence in C, right? Okay, this is only a sketch, but it's a nice way to apply, for example, this transfer principle. And in model theory, well, you will see next week a much interesting, nicer transfer principle that you will going to use in this Axe-Cauchy theorem. This is also a transfer principle, a way into transfer things from characteristic 0 to characteristic P, but at a much complicated level. Okay, but here you have an example of this type of idea, how to transfer things from characteristic 0 to characteristic P.
But the way you stated today, it holds in greater generality, or?
It does hold because, yes, there are versions of the Lefschetz principle which not only count sentences which are first order sentences, but properties that cannot be expressed by first order sentences. But then this is not in the scope of model theory. You need to do other stuff. But Lefschetz, there are variants of Lefschetz principle which can transfer properties which are not expressible in the language of rings. And you need either some other tools or prove something along these lines, but for another language or for something that can express these properties, right?
It's like embedding of fields. So if you have a property that only depends on algebraic geometry of algebraically closed fields, you have a countable amount of coefficients in the problem, you can create a field that is contained in the complex numbers.
I agree that the other proofs of the Lefschetz principle or the other Lefschetz principles are kind of built in this way. That's correct.
I mean, the problem for me is that it is difficult, to imagine what kind of meaningful statements actually are in the language of rings.
I totally agree. I mean, this is.
I mean, I think your step one not super, obvious, right?
It's well.
Well,
once you know
that it's okay, right?
I agree. There are not a lot of things that you can actually say in the language of rings. It is a miracle that you can you can give this example in a nice way, right?
You saw a proof of Javier, you just go with the proof of Javier and you replace that one with
I agree.
geometry reduction, and it's it works much more generally.
I totally agree. That I'm not claiming this transfer principle is the most useful thing in model theory, but it's giving you a flavor of what type of results you can use having model theory to transfer statements from characteristic P to characteristic 0. I'm not claiming this transfer principle is what you should use for the rest of your life, transferring things for but similar statements. Well, you will see next week similar statements that can help you to prove interesting theorem or transfer principles between 0 and P.
So I don't know if that's what we were discussing, but so the transfer principle is more like a claim about a language being in first order not being that strong than really strong theorem. No, like if you see that from the first moment, you can say, "Oh, it's incredible! I can do things." And it's like, no, this is really what it's saying is.
I agree. I mean, this is a point of view. At least
language is not that strong.
I agree. I mean, next week exactly. Next week you will see a transfer principle that allows you still to show things, but I mean to transfer interesting.
Is, okay, this is powerful. The second layer is okay, this is the language which is not powerful, and then there is a
I mean, to some extent, this is up to your perspective, right? If you really try to see what the sentences in the language of rings can say about an algebraically closed field, perhaps you will say, none of what I'm doing really in my mathematical life can be expressed in this language. I mean, I cannot talk about, I don't know, the homotopy of an algebraic group, the whatever. Then you will say this is a poor language, of course, because you're trying to deal with objects which, of course, exceed the expressibility of this language, right? But you can take another perspective and say, well, it allowed me to transfer at least something about the injectivity of polynomial maps. It's not too bad, right? I mean, I guess this is a matter of which objects you're interested in. And
so that it's not obvious that properties that you can express in first order language is expressible. Sometimes you have to define a notion, and you can really not trigger to see whether it's expressible or not in first order. Notion
I mean, the strength of the result is up to that. No?
exactly, absolutely, absolutely, absolutely. Okay.
But can you get away from having a complete theory? Because this proof was largely
The complete, yes, we use both things, right? We use the completeness and we use the compactness, right? We use these two things. Well, if you want to prove, I mean, I could have only said the result for these two theories instead of talking about C or FP, right? And here you don't need completeness at all. But it's nice. I mean, it's nice to state the theorem as things which are true in C are also true in FP, right? I mean, it rings the bell of mathematicians a little bit more if I just say you can transfer things from this theory to this theory, which doesn't look that appealing, right? But yes, if you state it just here, you don't need completeness, right? I'm not using it anywhere.
In fact, I think we use C and the algebraically.
No, we just use that.
In a strong way, no?
We just use that C is algebraically closed, right? But you care about C. I mean, this is an object that you care about.
Doing that thing was clickbait.
Exactly. That's correct. That's correct.
Well, the problem is that if you just can prove something in a P, right, you wouldn't know that it was in AC result.
Yeah.
Two.
So there's a question, right? If you have more powerful theory, right, which you don't speak on with, then proving things just over a P, right, won't suffice for this.
We go up to 11:15. That's the schedule, or 11 or
I think it's 11.
11.
What
No.
you like, I guess, right?
Okay, no.
Well, I have a meeting at 11, so I proceed.
For sure, no problem.
11, but I propose to decrease the break from 45 minutes to half an hour.
It's okay. We can start.
Stay with more things.
It was just in order to finish at the right time because I don't remember fully the schedule. Okay, now the next thing that we're going to think is about to talk is about products. We haven't discussed products at all, right? Usually when you're doing mathematics, you're doing groups, you consider subgroups, but you also consider products of groups, right? I mean, you usually consider a product in mathematics or a product of your structures. And products are very badly behaved in general in model theory, for example, but already in algebra, right? If you take the product of two fields, this is not anymore a field, right? Because you will have zero divisors, right? I mean, you have 0, 1 times 1, 0, it gives you 0. If you are doing just component-wise operation. So in general, it is not true that if you take two models of a theory, the product is going to be a model of a theory. This is not true. You can take two fields. There are models of the theory of fields, but their product is not anymore a field. That's kind of bad. You would like to define some product which, when you multiply your things, you still get a model of the same theory, right? this is what we will try to do. And to do this, we need to work a little bit. We're going to define ultra products. A great name for if the product doesn't work, then you take an ultra thing, right? This is the idea. So to do this, we need to define filters and do a little bit of right. This is kind of something we play with sets a little bit. So let me give you the definition. So let X be an infinite set. If you take finite set, this is not very interesting. So for the rest of this talk of today, X is going to be an infinite set. Non-empty, well, it's infinite, so it's okay. X is going to be an infinite set. We say a subset F of the power sets of X. So I have a subset of subsets of X is a filter if it satisfies three conditions. The first one is that it does not contain the empty set. So filters never contain the empty set. Okay. Second one is that it is closed under intersection. So if AB belongs to F, then their intersection belongs to F. And the last one is that it is closed under a superset. Yes? This is the power set of X. This is the set of all subsets of X. No, F is a subset of this one, right? And this is the collection of all subsets of X, right? Exactly. This is a collection of some subsets of X, right? And it is closed under a superset. So if A is an element of my filter and I have something like this, then B also has to be an element of my filter. Okay? So those are kind of strange objects if you want to think about them. They're closed under intersection, so you think they're going down, but they're closed under supersets, so they're also going up, but they don't go down up to the empty set, right? So you cannot have, for example, a set and its complement in a filter because their intersection will be there, and then the empty set will be there, right? Let me give you some examples of very simple examples. So the trivial. That's it. Okay. Let me finish some 5 minutes before so that you have time to get to your. So the trivial filter, which is just take F to be the singleton X.
They will come to pick me here.
Ah, okay. So I'll continue up to they pick you up. So the trivial filter, this is just, well, it's kind of trivial. It only has X, right? But more general, you can take if A is an element of X. Sorry, if actually I should say it like this. If A is a subset of X, then the filter, this is called the principal filter. Let me call it FA. This is just a collection of all B's such that B contains A. Right? This is also a filter. And we call this filter a principal filter. They called principal because it's kind of generated by just one element, right? Of course, this is going to be closed under intersection, and superset is defined like this, right? Of course, here I'm taking A non-empty, otherwise I'm not having a filter, right? And these are called principal. Does anyone can give me an example of a non-principal filter? Anything. X is not empty, it's infinite.
X set minus set of empty set, which is also filter.
Absolutely not. because you can have, in this set, you will have a set and its complement.
Okay.
And
in
since
this
it-
condition, you don't have any requirement for AB. Okay. So
Yes, this is, if the two sets are in the filter, the intersection is in the filter. You cannot just exclude the empty set because you will have sets which are not empty, their complement, their intersection, right? Let me write it. Perhaps this is instructive. So P of X, excluding the empty set, right, is not a filter since there are subsets A different than X and different than the empty set. And this implies that A intersection X minus A is the empty set, and this will be included in the filter, right? In this F. Let me call it U. So this cannot be a filter.
I guess you could take the open intervals, for example, from 0 to 1 over n. They are all like this. That's not principal, but that's also, but that's not, but generates a filter. Okay.
Interesting. Interesting. You're taking examples. So you're taking X to be the reals?
The reals.
Yes.
And then I will be generating a filter out of the intervals, open intervals from 0 to 1 over n. Yeah.
Take
Or yeah.
open intervals like this.
No, you just take a neighborhood of one.
Yeah.
Or this is the
But this is not the filter generated by one. No, it is.
you need I mean, for sure this is not going to be a filter, right?
No,
No, that's not
minus
going to be-
1 divided minus 1 and 1 n and equal to 1.
Minus 1.
Thinking of taking the
Okay, here.
No, that would be generated by 0. No, but that
No.
would be. No, I'm
This is not
talking about the
generated
filter.
by 0. and
I'm
this is a
talking-
filter.
I'm talking about the filter generated by those.
Right, but we haven't defined exactly yet what the filter generated by is. But
No,
okay, this is true. But you're taking this one.
No, this one is not. This one will be the principal filter of 0.
No.
If you take the filter generated by that.
No. Why?
Well, for sure this is.
The 0 is in every one of them.
No,
Yeah,
this is
that's
definitely not a filter, right? We need to,
Claro.
because we have, I mean, we need to close it at least under 3, right? We need all supersets of this. So in particular, for example, right, exactly. You need some closure procedure to make this a filter, but this is not a filter by itself, right? Because of course I need to add, in particular, I need to add silly things like just this set, right? For example, this one.
And I don't think this is a filter generated by 0.
No, of course not.
No, it is not. It's not.
No, it's not the filter generated by 0. For sure not.
Yeah, because
It's not. Okay, but before defining you what the filter generated by is, let me give you another example of a filter. Exactly. Good. This is called the Fréchet filter. This is the finite and cofinite, the cofinite sets. So the Fréchet filter is the collection, let me call it F Fréchet. This is just the collection of all A such that A is cofinite. A cofinite subset, right? Of X. Cofinite subsets are closed under intersection. A cofinite subset cannot be empty, right? Otherwise it would be finite. And cofinite subsets are also closed under supersets.
I know.
Yes, good.
So you take the
What is X? With an X precise X or X just any infinite set?
integer.
Okay. X takes Z.
And
Yes.
You take all subsets that contain one of them.
That's correct.
And And the following, so all subsets that
Contain
AN,
two,
where,
okay.
where AN is numbers divisible by 2 to the power n.
B such that B contains 2 to the n
Times something.
Times K. I see. For K in Z, and you apply this for each n. I think this.
That is indeed generated by the union of.
Right. I think this.
It's generated, but you didn't allow to see it.
I mean, I agree. he included the generation in the definition, right? I think this is going to be a filter, right? The intersection always contains one of these, right? So it's closed under intersection, right? It's not the empty set, and also by definition is closed under. I agree. This is another case.
Given a sequence, it always induces a filter.
I agree as well. If the you need to be careful because you need them to not be disjoint, right? If you take, for example, these sequences and the sequences of trees, right? If you take
what I meant is like you have a sequence and then you say that a set is in the filter if there exists a big index, so that that index.
I agree.
This is the filter of periodic convergence. Two-adic convergence, and the filter of Joel is the filter of usual convergence.
I agree. Okay, then perhaps we can stop for the moment, and then we'll see after the break how filters are going to enter into the picture. Okay. Cofinite means that the complement is finite. This means x minus a is finite. Okay. Nothing complicated to show that every filter F has the finite intersection property. Which I'm going to call the FIP. This is just every finite intersection of elements in F is non-empty. Finite intersection of elements in F is non-empty. Okay. Now that we have this property, we can ask if a given subset of subsets generates or not a filter. Okay. So this is easy. I'm very good. I started in a gentle fashion, so you haven't missed anything. So given, can I give a definition? Given a let me call it right. Given a set S of subsets of my set X, let the set this is going to set this is going to be a set generated by S, but we don't know yet if it is a filter or not. This is going to be the family closed by these conditions 1 and 2, but let me put it like this. This is just the union of A in S of the filter, of the principal filter FA. Right? FA is just this principal filter. This is just the collection of all B's such that B is a superset of A. Okay. And for S prime, where S prime is the closure under finite intersection. Let me put it here. This is all finite intersections and some integer and AI elements of S. So I first close S under finite intersections. I take all of them, and then I'm taking the union of all principal filters, right? If any, right? These are principal filters, and I'm trying to close it under intersection. But it could happen that here, perhaps I end up with the empty set, right? So what I'm saying here is a triviality, just a lemma. It's easy to show is that this set is a filter if and only if S has the finite intersection property. Okay, so whenever you have a collection of sets that has the finite intersection property, you can actually make a filter out of it, which is just the filter generated by T, right? Which is this thing.
What you have done is to define the topology by subbases, and now the filter is the sets that
you could right. This is a
generalization of what your element is.
This is a way to see it. You're thinking of these sets as the subbases, right?
Yeah.
And then you're taking all the unions of these subbases, right? But the only thing that you don't know is if this is really, I mean, subbases require more things, right? Like subbases requires that every element in X it has at least one element in the subbases which contains it, right? I mean, you want a topology, you want something that covers your whole space.
If you remember well, if you give me sets, if I take finite intersections and arbitrary unions.
Okay, but okay, yeah, I agree. You're going to get a subbasis. Well, you're going to get a basis because these are closed under supersets. So this is okay. I agree. Okay. At any rate, you really get a filter if and only if you get the finite intersection property. So for example, you can have topologies which are not filters, right? Because you can have topologies in which you have clopen sets and then the open and its complements both are open, but this should not be elements in the filter because you get the empty set, right?
If you have a topology and you select the point, you automatically.
Okay, good. Then this I agree. All right. Okay, now let me give you some examples. Right, now let me give you the definition, right? Definition. A filter F on this set X is an ultrafilter if it is maximal with respect to containment. With respect to inclusion, right? So this means I cannot add any more sets to this collection and remain a filter. Okay. Now, let me give you some observations, easy observations. Every principal filter is an ultrafilter. You want to think about it, it is not too difficult to see. If you try to add anything else to a principal filter, then it stops to be maximal, right? I mean, it's going to stop to be a filter. And any non-principal ultrafilter contains the Freches filter. Okay, this is exercise. You can think of them. They're not going to be used that much. But any ultrafilter which is non-principal, which is just not generated by one set, it has to contain already this filter about finite and cofinite. About cofinite sets. This has to happen. Well, you can think of this perhaps as an exercise. Okay. Now the existence of ultrafilters. This is a weak version of source and lemma. Okay? I won't give it, but this is the ultrafilters lemma. This is every filter is contained in an ultrafilter. This is an easy application of Zorn, right? I mean, just by Zorn, you're going to get one maximal element in the partial ordered set of filters under inclusion, and this has to be an ultrafilter. And well, this, you can show that this is a bit weaker than the axiom of choice. But, I'm not going to, since we're using the axiom of choice everywhere, I'm not going to do any details about how you really prove this lemma. But this is just Zorn, right? Okay, now let me give you another characterization which is a little bit more interesting. And this is a proposition that is going to be really useful. I mean, this is what we're going to use when defining ultra products and trying to prove that they really extend sentences. Is that you can think of an ultrafilter as a kind of oracle which really decides between sets. Like it's really going to tell you, if you give me a subset of X, the ultrafilter has to decide it is on me or it's not, or its complement it is. And this is kind of a way to decide. I think of them as an ultrafilter always decides between two sets, between a set and its complement, which one it is in the ultrafilter. So let me call this a proposition. The following are equivalent. One for a filter, let's say for a filter F. One is that F is an ultrafilter. Second is that if a union belongs to the ultrafilter, then one of them has to belong to the ultrafilter. Then either A belongs to F or B belongs to F. And finally, this is the same as saying that for every subset of X, either A belongs to the filter or the complement belongs to the filter, which is what I was saying. Okay, so these are both 2 and 3 are another way to characterize ultrafilters. This one is saying what I was trying to say. For any subset, it decides if the set or its complement is in the filter. And this one is very similar. Well, from 2, it's easy to see 3 because we can apply it to A union X minus A. So this is also kind of similar. It's deciding for a union if one of them has to be in the filter, and this is to be maximal with respect to inclusion. Okay, let me prove this because perhaps it's interesting to see that at least you will get the feeling of playing with ultrafilters a little bit. So we show the contrapositive. Okay, positive So we assume the negation of 2. So suppose we suppose that A union B is in the filter, but A is not in F, and B is also not in F, right? Right. So let us show. Okay, let me write it like this. It suffices to show that this set, that the set F, and put it like this, that the sets F union A and F union B have the finite intersection property. Right? Actually, this is not an and but an or, right? If any of these sets has the finite intersection property, then this means that I can take the filter generated by them, and then this means that F is not an ultrafilter because it's not maximal with respect to inclusion, right? Since this will show that F is not maximal. Okay, right? Because if it has the finite intersection property, then I know that there is the filter generated by this is a filter, but it will be an extension of F, which has an element which is not in F. So it's a proper extension, then I cannot be maximal, right? Now suppose none of them has the finite intersection property. Suppose neither this one nor this one has the finite intersection property. This means that there is a finite intersection between elements here and A and elements here and B, which is empty, right? But I need to use A because F is a filter. So A has to appear. I cannot have just a finite intersection from elements in F because I know this is non-empty, right? So there are C1, let's say up to Cn in F, right? And C1 prime up to Ck prime in F, such that when I do C1 intersection Cn intersection A, this is empty, right? And the same for B, C1 prime, all this intersection with B, this is empty. Notice that since F is a filter, already this intersection is in F, right? So I can only write just one C, right? Taking this to be just C and this to be C prime. Since this is in the filter, right? Since this is in F and this is also an element in F, what I have is that C intersection A is empty and C prime, intersection B is empty, right? But now we arrive at a contradiction because then now we have that C intersection C prime intersection the union, right? This one, well, this one is equal to C intersection C prime intersection A union C intersection C prime intersection B, right? But this has to be empty because this intersection is empty, right? And this has to be empty because this intersection is empty. So this is empty, but this is an element in F, and we assume that this was an element in F, a contradiction. We have two elements in the filter having intersection empty. This implies that the empty set is in the filter. This cannot happen, right? Okay, this shows 1 implies 2. 2 implies 3. It's direct, right? 2 implies 3 follows directly. This follows directly, taking B to be x minus A, right? Since X always belongs to every filter, right? So the union of A and X minus A is the whole set, which always belongs to the filter. Then one of them has to be in the filter. Then for 3 implies 1, I think we also want to prove the contrapositive, if I remember. Also the contrapositive. So we assume F is not maximal. So if F is not maximal, take A, which is a subset of X, such that A is not in F, and I want it such that better, sorry. Right, exactly. It's not maximal. Let me write it like this. If this is not maximal, let G be an ultrafilter containing it, a proper ultrafilter. By the ultrafilters lemma, I can always find one, right? And now let A be an element in G, which is not in F, right? Since this is a proper subset, there must be some A which is in one and is not in the other, right? But if right, since G is a filter, then we cannot have, this cannot belong to G, right? Because A already belongs to G. So I cannot have both belonging to G because otherwise the empty set would be in G and this is not a filter. So this one is not in G. So since F is contained in G, this one is also not in G. Hence, X minus A is also not in F, right? And that's it. We just proved the negation of 3, right? Because sorry, we proved the negation of 3, right? We just showed that there is an element A which is not in F, and its complement is also not in F, right? Which is the negation of 3. Okay, so filters from sorry, ultra filters are those filters that precisely decide whether a subset of X is in the filter or is not in the filter. Okay. Now let me define you products and ultra products, and we're going to see where we're going to use these filters and ultra filters. So definition. Let Mi or I be a collection of L structures. Okay. I'm going to define it the product. So we define a new L structure M, where the universe of this structure is just the product of all the Mi, and I need to tell you how to interpret the functions, the constants, and so on, right? And I'm going to use this notation. So I'll write and then explain you the notation I'm using. So let me see, where we use an element, the notation. I'm thinking of elements here as functions from I to the union of this collection, right? An element A in M, we see it as a function A from I to the union of all Mi, such that, of course, AI belongs to Mi. Okay, this is the notation I'm going to use for elements in the product, right? Instead of indices, I'm going to think about this. This is the ith coordinate of my elements in the product, of my element in the product. Okay, is this clear? Right. Right. I mean, if you think of the product of M1 times M2, what I'm saying is that I'm just thinking of this as a function from 1, 2 to M1 union M2. And then, of course, A of 1 has to belong to M1, right, for example. So this is just another way to write an element in the product, but it's a little bit easier to write it like this for what I'm going to write right now. Okay. So I need to define you how to interpret the function symbol, the relation symbols, and so on. And well, there is the more natural way is to define it as follows. So functions, I want to define them coordinate-wise. So the interpretation of my function is just how I interpret each function on each coordinate, right? So for G, a relation symbol, right, of arity N, let's say, then I'm going to say that the interpretation in this new structure of A1 up to AN, we call this AN. Exactly. This is a function. Oh, sorry. Thank you. This is a function symbol, and A1 up to AN are elements in this product, right? Then the interpretation of this is just the interpretation of Mi at the coordinate A1I, and the same thing for each one of them. Sorry, this is G. G of like this. This is better for I in I. So this is I'm defining this here an element, right? Is this clear? Shall I perhaps use a different notation or?
You have the perspective
You're right. Okay. Let me write it like this. Yes, this is better, right? So this is an element, which means it should be seen as a function. If I evaluate it at I, this is the same as evaluating at this tuple the function mi. Okay, this is the same as in groups, for example, taking the product of two groups, saying that the product in the group, the operation in the product is just coordinate-wise the operation that you have in the group. This is exactly the same definition. This is just coordinate-wise, the coordinate-wise application of each function, right? For a relation symbol of arity n, we say that this tuple a1, an is in my relation if this happens for all I. If and only if for every I, it holds that a1 of I, an of I, if this tuple is in the relation in my structure mi. Okay, so the relation has to hold in all, exactly all structures mi, right? And finally, for a constant symbol, the interpretation of this constant symbol, this is a function, right? So if I evaluate it in I, this better has to be the constant symbol in mi. That's it. Right? I'm saying this is a function, but I am evaluating this function, and this is precisely the interpretation of that constant symbol in mi. Okay. So this is the product. This is how we define the product structure. Okay. Now, this product, as we saw, is not going to satisfy all the sentences that are true in each of the mi, right? For example, if we take the product of, as we said, if I just take I to be just 1 and 2, right? M1, M2, two fields, then the product of M1 times F2 is not a field. So products don't preserve all sentences, unfortunately, right? However, they do preserve atomic formulas. This is true. Okay. So let me first give you a perhaps give you a lemma. Right. Okay. You need to. Let me put it as an exercise. Okay. You need to prove something for terms, but this is also not too difficult. Lemma part 1, let's say, part I is that if t x1 xn is an L term, then the interpretation, I'm going to keep for the rest of this part all the time this M is the product of all this MI, okay? I'm taking M is going to be my product of a collection of structures. Then the interpretation of this term applied to A1, AN And then here my I, right? This is, we know that this is, each term defines a function in my structure. And I am evaluated this term at elements A1, AN in my product M. Then this has to be also an element of my product N. So this is a function, right? So this is also the same thing as evaluating the term at every I, okay? So evaluating this term at I is the same as evaluating the term at the coordinate I, okay? This is going to follow by induction on terms and the way we define the functions. No, nothing too complicated, and the constant, okay? And part 2 says that if phi of x1, xn is an atomic formula, an L atomic formula, an atomic L formula, let me write it perhaps right like this. Then for every A1 up to AN, let's call this A, right? They write it like this in my product M, right? We call this M is the product of the MIs. It holds that M satisfies phi of A1 up to AN if and only if MI satisfies this structure. MI satisfies phi of A1I up to ANI for all I in I. Okay, so this is basically saying that if you have a product for atomic formulas, the satisfaction relation in my product is essentially just being satisfied for every I at every coordinate, right? I mean, you're just basically saying that for atomic formulas, satisfaction is the way one would dream, right? It's just being satisfied in the product is just being satisfied on each of your structures of your product, right? But we know this cannot hold for sentences because otherwise the product of a field would be a field, right? This cannot hold for more than atomic, right? This only is happening for atomic formulas. If we go a little bit up, then this won't work if we just take here sentences, right? Because, well, it's just not true, right? We can express in a sentence to be a field, and the product of two fields is not a field. So if we want to extend, or if we want to try to prove this lemma, here changing atomical formulas to general formulas, then something has to be done. We need to amend this in some way, right? And here is where filters are going to play a role. We need to quotient the product by a nice equivalence relation that is going to make everything work. And this equivalence relation that we're going to define is going to be defined with a filter. Okay? Okay. Okay, so this is a definition lemma, right? Is that, so let I be an empty set and F be a filter on I, okay? Let also MI, I and I be a collection of non-empty sets. For example, think of them as universes of structures, right? then the relation on the product of the mi's given by two given elements of my product are equivalent modulo my filter B. This is if and only if the set of indices in I for which the ith coordinate of A and the ith coordinate of B are equal has to be an element in the filter. It's an equivalence relation. Okay, so let me try to parse you this in a nice way. So recall that a filter always contains the whole of the set I, right? So if, for example, this set is such that A is really equal to B, right? Then of course, all the coordinates have to be equal, right? Because these two elements are equal, so all the coordinates have to be equal. This is for sure included in the filter. So at least this relation contains all the pairs which are equal. The actual pairs which are equal they're in the relation, right? But it might also contain, I mean, two pairs are going to be also in the relation if, with respect to the filter, those coordinates in which they agree belongs to the filter, right? One way of think of this, of filters, is this. I should have said this. Perhaps you can think of a filter as saying something like the elements of the filter are the big sets, right? You think of the filter as, if I am a member of the filter, I'm a big set, right? This is the kind of way you can think of the filter. And then this is saying if my 2 points of my product agree for a big set, then I'm going to treat them as equal, or I'm going to treat it as at least as related by my filter, right? So I'm trying to relate elements which agree for large sets, for very big sets, where being large or being big is just I belong to the filter. Okay? That this is an equivalence relation is an easy exercise. You just use the properties of filter to show this, right? I mean, to show that it is reflexive it's trivial. To show that it is symmetric, I guess, as well, right? And transitivity, you're just going to use that is closed under intersection, I guess. Perhaps you don't need, oh no, you use both intersection and closed under superset for transitivity, but it's definitely an easy exercise. The proof is easy exercise. Okay, so now we're thinking of if you quotient, let's say if you quotient this set under this equivalence relation, you just put under the name under the same class sequences for which they agree for large sets of the filter, right? Yes.
I didn't pick the intuition.
Okay. So the intuition is think of any set that is going. I mean, the large sets are the ones which belong to the filter, right? I'm taking a filter and I'm saying a set is large if it is in the filter, right? And the equivalence relation is now saying if these two elements agree on a large set of coordinates, they should be equal, right? For example, if my filter is the filter of Frechet, which was the one of cofinite, I'm saying these two sequences of elements of my product, they only disagree for finitely many coordinates. Then I'm saying, okay, they agree really a lot, right? They agree on a very large set. This is what I'm trying to, this is the intuition perhaps one can have in mind, and this is a useful way to think into these filters, right? Yeah. Okay, now we want to quotient a given product by this equivalence relation and define now what the structure should on the quotient, right? I define you first what the structure is on a given product, right? Now let me define you how to define the structure on this quotient, right? And this is what we call the reduced product. So
this, if we take the filter of neighborhoods that you already said, these are functions agreeing in the neighborhood.
absolutely. Absolutely. So these are what? Germs?
Yeah.
They are germs.
Exactly. Absolutely. These are exactly germs.
So the quotient by equivalent relation are the germs.
Absolutely. In this case, these are just the germs. That's fully correct. I totally agree. Okay, now let's define the reduced product, the reduced product. So definition, again, we have this collection of L structures, right? And we have this M, which is defined as the product, right? I told you how to define this structure M, right? This was the structure where the relations were defined as it has to have holding every MI. The functions were defined also coordinate-wise, and the constants also coordinate-wise, right? Let now F be a filter on the set of indices, right? Which we assume non-empty. I mean, we're at least having some structures there, right? Now I'm going to define you something. We define a structure. This is called the reduced product. The reduced product, let's say with respect to F, as follows. And we call this, we note it like this. This is M quotiented by F. This is called the reduced product, right? This is the structure I'm defining. Let me call it for the moment M prime, okay? I need to tell you how to interpret the relations, the functions, and the constants in this new structure, right? So of course, the universe of this new structure is precisely the product quotiented by this equivalence relation. This is the universe of my new structure, okay? Yes, since we proved that this is an equivalence relation, I'm taking as a universe the product quotiented by our equivalence relation. Now I need to tell you how to interpret the relations, functions, and constants. This is actually a definition, also lemma, because we need to prove that some of these definitions are well defined because we're using equivalence classes, and we need to prove that this does not depend on the representatives I'm going to give you, but I won't do all the details. This is actually in the notes, so you can read it after if you want. So let me do it first for a function symbol. So for let's say G, again a function symbol of arity n, right? Then we need to know what this element is, right? I mean, I need to know what G, let me put it like this, M prime A, well, shall I add a notation? No, okay, let me do it like this. A1 modulo. Let me write this for the equivalence class of A1 modulo this relation. Instead of putting the whole thing, let me just put F, okay? Is that okay? I need to tell you.
Can I interrupt and make a general question? I think I am getting confused.
Yes.
I can remember some.
It's okay. It's okay. Okay. Go.
When you construct products.
Yes.
In mathematics with respect to an inverse, to some. When you construct limits in mathematics, you usually take the product of all the structures and then you take a subset and not an equivalent relation. So
Absolutely.
This is not a product. So usually,
but you take an equivalence relation for one of them. So for inverse limits, you take a subset, but for direct limits, you take an equivalence relation.
Direct sum, not direct product. So it's like a hybrid. This is very.
I think you do. I think you do. You don't take direct sum necessarily. You take full product and then take an equivalence relation.
Is that this generally?
I think so too. Joel will look up, but
I'm checking because I was exactly the same thing.
Yes. So
can we clarify? Because this should fit with general.
I
should remember.
I think in general you will get just a product and an equivalence relation. But actually you get an equivalence relation. Sorry, you get an equivalence relation, but in the union, no?
Yeah. This is what I say.
Exactly, an equivalence relation in the union.
And a subset in the product.
I agree. This is something else. You're right. Sorry. Yeah. Sorry. This is not. It is not right. It is not an equivalence relation in the union, nor a subset of the product. You're correct. This is an equivalence relation in the product. But this is the way exactly the same as germs, right? Germs are not germs set an equivalence relation in the product, right? You can.
And this is really a different thing. You don't have maps between the MIs, or limits in the maps between the MIs.
Yes, here we don't have any map. Well,
So
yeah, you're right. Here we don't have yet any map.
So in this various product, we won't get maps from M prime to any MI.
Well, you have natural maps.
From MI to
Yes, you have natural maps from MI to M, right?
Yeah, MI.
And actually, you have also a natural map from, you have the projection map, right? I mean, this still exists as a map just from the product one, right? Yes, after the quotient, this map makes no sense, right? You will need that representative. So you will need that section, yes.
The natural thing is that the product sends maps. No, receives.
Both, right?
No. There is one universal product. There is one universal.
Right.
Well, it's universal with respect to objects that receive map, no?
Yeah.
So
If you have some object that receives map from all MI,
no, that's for the column.
This is for the column.
Yeah, I agree.
For the limits.
So the fiber products in algebraic geometry sense
So
maps.
everything maps to the limit.
Okay, so let me continue with the construction. But I agree, it's not a projective nor direct limit. So I have a function symbol, I have n elements which are equivalence classes. I need to tell you which equivalence class is going to be its image, right? And I just take the equivalence class of the image of any of these representatives, and this is going to work well. Okay, so this is G M, where M is just the product, right, of A1, AN, and the whole thing modulo F. Okay, and this, of course, I've used in here representatives, but you can show that it won't depend on the representative. Okay. Here, to show that it does not depend on the representative, we need to use something about the filter. We need to use something about the equivalence relation, but it's not too difficult. You can check the proof in the notes. Right, and finally, if not finally, but for a relation symbol, this is the point where it gets important. So for a relation symbol, of arity, let's say of arity, and we're going to say that these elements, this equivalence class is A1 modulo F, AN modulo F, belongs to the interpretation of my relation. Here we put if and only if. Before, recall in the product was if this relation was happening at all the MI levels. Here we're going to put something different. We're going to put it happens at all indices of an element of the filter. So this happens if and only if the subsets of indices such that A1 of I, AN of I is in the relation in my structure MI if this belongs to the filter. So this is very different than what we were having in the product. Then now it really depends on the filter, right? We're saying those equivalence classes are going to be in the relation if the set of indices for which representatives belong to the relation in the corresponding coordinate I, if this set of indices belongs to the filter. So if you want to think about large again, this is saying the set of indices for which this relation holds has to be a large set, right? This relation holds for a large set of indices in my structure, right? This is the kind of difference from what we were saying in the product. In the product, we were saying this set has to be equal to I. And here we're saying now, okay, we relaxed it a little bit. It only has to belong to my filter, okay? And again, one has to prove that this does not depend on the representatives. It's not too difficult. Right, I think I didn't say it for a constant, but for a constant, we are forced to define it the same way, right? If C is a constant symbol, then the interpretation is just the interpretation in M modulo the filter. Okay, there we have no choice. We have just to take the interpretation and quotient it by the equivalence relation. Okay. So right, you need to prove, of course, that there is a proof that I'm skipping is that this is a well-defined structure because I use representatives, but this is an exercise that one can write. It's not too difficult. Okay. So let me put these two lemmas because one is okay. Lemma one is that this is well-defined. It does not depend on representatives. And part two of the lemma is that you recall that we proved that we proved something for the product. I mean, we proved. I announced as an exercise to prove that if I have a term, the interpretation of the term is basically just coordinate interpretations of the terms, right? We need to show an analog for this one, and it's the following. If T, let's say of x1 up to xn is an L term, right? Let me put it like this, then T in this M prime, right? In this model of some classes A1 modulo F, AN modulo F, this is also just Tm of A1 AN, the whole thing modulo F. Okay, so it holds for functions, right? For functions, we define it exactly like this, but the same is going to work for more generally for terms. Okay, the interpretation of a term given elements of my reduced product is just the equivalence class of the image in the usual product. Okay, so this property of the function, I mean, the way we define functions is going to impose that this happens also for terms. Okay, this is use induction on terms. It's not difficult. Okay. Now with all these lemmas, we can prove now the main theorem of ultra products, which is the following. Oh, I should have, right, perhaps. Right. Okay. Let me give you two lemmas. Perhaps we can prove this one. We have time. Lemma 1 is that, let me call this lemma 2. If phi of x1 xn is an L atomic formula, and A1 up to AN are elements in M, which is my product, right? Then my reduced product satisfies this formula for these equivalence classes. If and only if, what should I put in this side? What do you think? What should be your guess? So this formula is going to be, this is an atomic formula, but this formula should be satisfied in the reduced product if and only if what? No, this was true for just M like this, just for the product. But for the reduced product, we have something better. Exactly. If and only if the set of coordinates where this holds, A1I and I, if this belongs to the filter F, sorry. Right, so now the truth of an atomic formula is not if it is true in every coordinate, but if the set of coordinates in which is true is a large set, right? This is the change of point of view now that we divide by the filter, okay? It's a nice way to have it. Now, unfortunately, this is not true again for general formulas. But the only problem actually is negation. If I would like to now, let's say, try to prove that this holds for every formula, and I do induction on formulas, right? I'm going to get stuck at the very second step. Like I proved it already for the base case, which is atomic formulas. This is okay. We can try to prove it. And then I want to assume it holds for a formula psi. I want to prove it holds for its negation. Then having a filter, it's not going to tell me anything about what happens for the negated formula.
So negation was the only problem before with the product of the
as well.
You can take the trivial filter.
As well. So
the problem is that the filter is not going to contain the complementarity. Right?
Exactly.
Okay.
We don't know. We don't know. If for example, if we know, well, let me write it, right? Suppose, for example, that, so suppose we know that this one satisfies precisely this, right? This one satisfies phi of A. I'm going to, for the moment, just write A. I'm going to write it like this instead of a tuple of, just in order to write less. Suppose that we know this. Right? And now we want to show the same thing, but for the negation, right? Suppose now we want to show, sorry, This is what we want to show. This is what we don't know, right? Here I put I, mi, the negation of phi of ai is in the filter, right? How do you use the induction hypothesis to prove? I mean, how do you use this one, which is your induction hypothesis, to show this one, right? So let's say I start from this direction, right? If I start from this direction, then I would start, okay, if this is the case, then this implies that M does not satisfy phi of this one, right? This is how I would try to do this proof. Okay, if I satisfy the negation, then I cannot satisfy this one. Okay, then by this implication, by the induction hypothesis, this implies that this set I, the set of formulas where Mi satisfies phi of ai, this is not in my filter, right? But how do I continue? I only know that something is not in my filter, but I'm stuck. I have no idea how to continue, right? However, if we knew that this filter is an ultra filter, then we do know stuff, because we know that this set or the complement has to be. So if F is an ultra filter, then if this is not in F, we know that the complement is, right? And then the complement, I mean, if, let's say, if F is an ultra filter, right? Under the assumption that this is an ultra filter, knowing that this set is not in F, it means that the complement is. This implies that the set of indices, I mean, the I minus this set is in the filter, right? But what is this complement? Well, the complement is precisely those indices in which this formula is not satisfied, right? So this is equal to the indices in which Mi is not satisfied, but this is the same as satisfying the negation. And then this is what we needed to prove, right? So in general, if I only take a filter, here, I can only do this lemma for atomic formulas. But if I take an ultra filter, then I can do this lemma for every formula. And the proof is actually what I just wrote. I need still 3 more cases to show that this also holds for the conjunction and for the existential. Let's do it, and we prove the theorem, right? Let me write the theorem here, and we show it. This is actually an actual theorem. It's called Wash theorem. Wash's theorem. This is the theorem of Wash, and I think it also has, right, it has also a Polish guy, and this, you pronounce it like a W. This is like this, Wash. So it says the following, right? Let me write it completely so that you have it. Let Mi be a collection of structures, of L structures. Let me just think for a second. Right. And I, right. And F. An ultrafilter on I. Let phi of x1 of 2xn be an L formula. And A1. Yes. Yes.
So we assume that quotient by F does not imply.
Right. I only did one implication. We can do the other one. Sorry.
You only did one implication.
I only did one, but the other one it's the same, right? I mean, if now I have that this is in the filter, right? These two are the same. You agree? I mean, this is just these are just the same. Then if this is in the filter, the complement cannot be in the filter. This is just by filter. I didn't use ultrafilter, right? This is just using it as a filter. And if this is not in the filter, this is just also the contrapositive of this implication, right? So actually the arrows are now double implications everywhere. So if I have if I have an L formula and these elements here, then this reduced product with the ultrafilter satisfies phi of A1 of these equivalence classes if and only if the set of indices in which this formula holds belongs to the ultrafilter. And now this is any L formula, no restriction, right? Let me quickly sketch the proof. Proof, we proceed by induction and formulas. See, I know at the beginning of the lecture, this idea of formulas and so on is silly, but the fact that we can do this silly procedure of doing induction it's used everywhere. It's really useful. I mean, we proceed by induction on phi. The base case is just phi is atomic, but this is this lemma, right? Base case phi atomic is lemma 2. Okay, we haven't proved it, but this is not the difficult part because atomic formulas, they're reduced to relations, and the relations were defined basically exactly like this. And equality of two terms, this is basically how we define the equivalence relation. Perhaps I can do this later, but let me, for the moment, suppose that we have already proved it for atomic formulas, okay, that we have already done this lemma 2. This is the base step of showing this theorem. Now suppose that we have it not only for phi, but for two formulas, right? Well, actually, okay. Now the inductive step, right? Inductive step, we need to show three things. We need to show it for negation, we need to show it for conjunctions, and we need to show it for the existential quantifier, right? For negation, this is the proof, right? For negation, we already did it. Now for conjunction, this is actually for conjunction, we don't need ultrafilter. This is only going to use filter properties. I think actually negation is the only problem. This is the only point where we actually need an ultrafilter and not a filter. So induction, let me write, we already proved it for the negation. So for negation, we did. So suppose the result let's write it like this for conjunction. So suppose, let me write it here. Perhaps this is my property star. Suppose the star for formulas psi1 of x1 up to xn and psi2 of x1 up to xn, and suppose that phi is psi1 conjunction psi2, right? We need to show the result net for this new formula, right? So if we satisfy phi of A1 up to AN, their equivalence classes, right? This is by definition. This is just the definition of phi. This is just saying that M satisfies both psi1 of AN of F and it satisfies also psi2 of all these elements, right? You agree? The and. Now this is if and only if by the induction hypothesis, right? Because we assume this holds for these two, that the set, let me call it A0, the set of indices where this formula holds, right? A set of indices for which Mi satisfies the formula psi1 for A1i up to ANI. This is in the filter, right? This is just the induction hypothesis applied to a star applied to this formula, psi1, right? Now I apply it to psi2, and I get that another set of indices, perhaps this is a different set, but still it's in the filter. A1, I, up to ANI, that this is also in the filter. But since this is a filter, A1 intersection A2, this is if and only if, right? If and only if the intersection belongs to the filter, right? Note that in this direction, I'm using that the filter is closed under intersection, right? So this intersection has to be in the filter. You agree? And this other way is because filters are closed under by supersets. So if this is in the filter, for sure, these two need to be in the filter too, right? But now let's see what does it mean that this two is in the filter. Is that the set of indices where both formulas hold is in the filter, but this is exactly saying that the conjunction, the set of indices where the conjunction is true is in the filter. This is exactly the same as saying that the set of indices where Mi satisfies both psi1 of A1 up to AN, all of them, of course, and psi2. Let me don't write it. If this belongs to the filter, which is what we wanted to show, right? Okay. Now it remains to show. We have 10 minutes or so. Let me don't erase the star. Let me show it for the existential. This was NF, right? Now let phi be the formula. There exists some y theta of x1, xn, y, right? And suppose star holds for theta. for this formula theta of x1, xn, and y, right? Now, if M satisfies this, there exists an x theta of A1 modulo my filter, AN modulo my filter, and y, right? Sorry, this is an exists y. Then this is just by the definition of how this relation is defined. This means that there is some B, let me put it like this, some class, right? In this I mean, there is an equivalence relation such that, well, this formula holds for all these elements, right? But then we use induction, right? And by induction, this is induction hypothesis, says that the collection of I for which Mi satisfies this formula, A1 of I, An of I, and Bi, that this is in the filter, right? Then the collection of formulas which is going to satisfy the existing X is a bigger set. It can be a bigger set, right? Because in particular, in all these structures, if there is one Bi, well, for sure the formula there exists some Y such that this holds is true, right? So note that let me call this set A, let me call it B, right? Let's call this set over here, all this set, let's call it B. Now note that B is a subset of the collection of all indices such that Mi satisfies that there exists some Y such that phi of A1I, ANI, Y. Right? Because, well, if I have an index here such that this holds, I already have a witness, right? So for sure, this formula has to be true, right? It might be true also in other indices, but at least it is a superset. This means that this one has to belong also to the filter, right? Because if this belongs to the filter, this has to belong to the filter because filters are closed under supersets, right? So this gives this implication, right? If this set is in the filter, then this set has to be in the filter, right? And now I need to do something for the other implication, right? I still need to do something for the other implication. Let me think if I'm missing something. Well, no. That's also easy, right? Right. For the other implication, let me do the other implication. For the other implication, then let Bi, sorry, so assuming this is true, I'm going to take solutions and then I'm going to define an equivalence class out of these solutions, and this has to be a solution of my set. Let me write. Assuming that this set, let's call this set C. Assuming C is in the filter, right? Let for each I in C, Bi in Mi be such that mi really satisfies the formula phi of a1i, ani, and this b sub I, right? Because
Not B sub I, B parentheses.
right, but I haven't defined what the function is. This is actually an element. So since I know that this is true in my structure mi, I take a witness.
Then B super.
Okay,
But otherwise.
B super I agree. It's okay. It's just an actual element in this structure. For the moment, I don't have an element in the whole product. I only have an element, but for I here, right? Now define the following B. This is actually going to be a real B in the product, right? In the product of the mi's as follows. You take B of I and you define it as follows. It is going to be your B super I if I belongs to C. And otherwise you take any element, pick any element. Just let me call it just any element in mi. Right? Then, of course, we have that m modulo f satisfies the formula phi of a 1 modulo f, a n modulo f, and finally b modulo f. Right? Because we know if this was not the case, then the set of elements here for which this does not hold won't be in the filter. But we just have shown that it has. By construction, it has to satisfy. Sorry, this is theta. We use induction by induction, we know that this has to be satisfied. Okay.
The Frechet filter was an ultrafilter.
No. Every ultrafilter contains it, but Frechet filter is not an ultrafilter because it does not decide. If I take, for example, the Frechet filter in the natural numbers, it does not decide you if it does not contain even nor odd. Right? Every ultrafilter contains the Frechet filter, but Frechet filter is not an ultrafilter. Actually, we don't know any ultrafilter in N. I mean, we know there exists Poisson's lemma, but I cannot give you any. I cannot present you any ultrafilter. Right. I mean, unfortunately, I cannot give you constructively a non-principal ultrafilter. Sorry. Ultrafilter, I can give you the ultrafilter generated by the subset singleton 2. This is an ultrafilter, but a non-principal ultrafilter, I can't.
And we do an exercise because
Yes,
so
sure.
to take an ultrafilter, and so we should take as many copies of the complex numbers, for example, and we should prove it is a field.
Let's even do something better. I think this is the kind of thing you're going to do. Look at this. Let's use this theorem for a second. So in particular, this can be used for sentences, right? This is implying that a sentence which is true in a large set has to be true in the ultra product. By the way, of course, this thing when f is an ultrafilter is called the ultra product. I forgot to say the most important part of the name. This is what is called the ultra product. So the ultra product is the reduced product. So the product quotiented by an ultrafilter. This is what is called an ultra product. So a consequence of Walsh's theorem is that if you have a sentence which is true in a large set of indices, it has to be true in the ultra product, right? Where large means the set of indices belongs to the ultrafilter, right? So let's think for a second this ultra product. Consider let f be some ultrafilter in the set of primes. This is the set of primes, prime numbers. Okay, this is an infinite set. I take a some non-principal. I want it to be non-principal. Some non-principal ultrafilter in the set of primes. Okay, and now consider the following ultra product. Let me call it K. This is, I consider the product of all algebraic closures of FP, right? Modulo this filter F, right? Now let us think what kind of field is K, right? It has to be a field, right? Because each one of these, right, satisfies the sentence of being a field, right? So this means that, let me write it. The set of indices, I mean the set of primes, right, for which FP alg satisfies the formula of being a field. This is the whole of P, right? Because each one is a field. So this is for sure an element of, this is for sure an element of my filter, right? Since each of these sentences is true in all, and this is an element of my filter, this theorem says K also satisfies being a field, right? In fact, this field has to be algebraically closed, right? Because all of them satisfy the sentence a degree of polynomial D has to have a root. So this is also going to be true here. Now let us think, what is the characteristic of K? Is of characteristic 0. Because, well, let's think. The characteristic of K, let me put it like this, characteristic of K is actually 0. Here's where I need no principle, that's correct. Otherwise, this is going to be just one of the FPs. That's correct. This is where I need no principle. So let me write it. With this we can perhaps almost finish for today. So now look at the sentence. Let us have a name for it, because look at the sentence theta p, which is just 1 plus 1 plus 1 is different from 0. This is p times, right? Let us look at the collection of indices, right? The primes, such that FP satisfies this formula. Oh, sorry, using too many P's. Okay, this is for a Q, for Q fixed, right? For Q a prime fixed, let us look at which primes satisfy this formula, right? This is actually only one, right? Only when P equals Q, because no other FP can be of characteristic Q, right? This is only just FQ alg, which is finite, right? This means that the complement, I mean, a finite, since we're non-principal, right? We contain Fréchet's filter, right? This was this exercise. So this cannot. This. Oh. Thank you. This is just Q. Thanks. This cannot belong to the filter, right? Because we know that since this is non-principal, it contains freshest filter, so it contains every cofinite set. But then it contains also the cofinite set not having Q. If it were there, then I contain the empty set. So this is not in the filter, right? This means that the collection, the complement, right? This means the complement is in F, right? But the complement is the set of primes such that FP alg satisfies the negation of theta, right? This is in F. Perhaps I should have sent this directly, right? This set has to be in F because, well, there are actually cofinitely many primes that satisfy this sentence, right? But this means that this is true in K by the theorem, right? Because if a set of indices satisfying a formula is large, this formula has to be true in K. So this implies that K satisfies the formula not theta of Q for every Q. But this is exactly being of characteristic 0, right? So actually K, the ultra product with respect to some non-principal ultra filter of all the algebraic closures of FP turns out to be, it's actually C. Who said C? You're right. It's actually isomorphic to C, but for this we need to know what is the cardinality of this. We haven't really specified. If we prove that this has cardinality the same size as the complex numbers, then by Steinitz theorem that we saw previously this week, we will know that this is actually isomorphic to the complex numbers. This is true, but we need to first show that this has the right cardinality. But at the very least, we know that it is a model of algebraically closed fields of characteristic 0, right? It's an algebraically closed field and it has characteristic 0. This is another way. This is another way to see perhaps the transfer principle, right? Because you're saying formulas that hold for all but finitely many primes in these models need to hold in a field of characteristic 0. The way we, I won't prove it because I think we're lacking time for preparing you for next week. But if you look at the notes, we use ultra products in the notes to show the compactness theorem. So the compactness theorem can be proven by a clever way of using ultra products. So this, right. I'm afraid I mean, in the notes it's like 2 paragraphs or 3 paragraphs. We have done the work. It's done kind of in this Walsh's theorem, and then using Walsh's theorem, one can deduce compactness in general. Right. So you're going to use ultra products next week for sure, at least in the course of Christian. You will see. Right. You're going to use ultra products at some point. So this is a nice construction. In general, it's a construction that is used very much in I mean, for group theorists, you use it a lot to construct interesting groups which are just ultra products of finite groups. You just start in, okay, here I started with just algebraically closed fields, but you can try to think what kind of strange field, for example, is just the ultra product of all finite fields, right? This is going to be a strange object, right? It's a field of characteristic 0, but which encodes what is true in almost all finite fields. Right? Perhaps I should put ends here as well. Doesn't matter. Those are called pseudo-finite fields. And if you take ultra products of also some finite groups, that's a good exercise. Think of what happens if you take the ultra product of all these groups for some non-principal ultra filter over the natural numbers. This is interesting. You should get something that you know at some point. That's an interesting object. And in general, if you're taking ultra product of finite structures, this is something which is much studied in general. Yes.
Did we prove? No,
I did have a whole of holes in these proofs.
We take now the Reshev filter.
Yes.
Construction.
Mm-hmm.
I think we have proven that we obtain a ring characteristic C. Oh, well, no, not a ring.
Yes, a ring, because a field cannot be expressed
but also a ring
without quantifiers.
The ring also needs quantifiers.
Yes, but only universal quantifiers. So
we know that it is a ring.
You're going to get a ring just because it is an L structure, which is a substructure of a field. You're going to get a ring. This you know.
So we have proven that we get a ring of characteristic 0, and in order to get a field, then we need to pass to ultraviolet.
Absolutely. The reduced product, just the reduced product, is going to be a ring of characteristic 0. You're right. That's true.